Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 7, Differential Equations. Today we're doing the Chapter 7 review. A reminder that today is going to be a calculator lesson, so you might want a graphing calculator for what we're about to do. And also a reminder, in AP Calculus AB, you always want your calculator in radian mode, and you should be rounding to 3 digits after the decimal place. Enjoy today's notes. All right, everybody, welcome to the Unit 7 review on differential equations. Reminder that reviews do not cover all of the material from lessons, but will hopefully remind you of key points. To be prepared, you should be studying all of the packets from Unit 7, but overall this should give a good review of the main topics. Let's get right into it. Number 1, consider the differential equation dy dx is equal to y squared over x, where x is not equal to 0. On the axes provided, sketch a slope field for the given differential equation at the 8 points indicated. All right, common AP exam style problem where they ask you to sketch a slope field. We see the 8 points that are listed here. Conveniently, they did not give us any of the ones on the y-axis because those are places where x would be equal to 0, and we see that the slope would be undefined at those points. Where I generally start for these is I'm looking for places where the slope is going to be equal to 0, and I notice that because y squared is in the numerator, that if y was 0, that would make my slope equal to 0. So the places where y is 0 would be anywhere that's on the x-axis, right? If we think about these coordinates, this would be like -2, 0, -1, 0, 1, 0, 2, 0. All of these are places that have horizontal tangent lines, because if we plugged in the x and y values into our slope, we would be getting 0 for each of these values. Now I only have 4 points left, and my goal here is to take the x and y and to plug in and to see what I get. This is the point 1, 1. If we plug in 1 for y and 1 for x, we get 1 squared over 1, which is 1. So I'm going to draw a little slope line with a slope of 1. If we plug in the point 1, -1, -1 squared is +1, 1 over 1 is 1 once again, and so we should see 2 lines that have the same slope at these 2 points. If we go over here to -1, 1, we would have 1 over -1. That's going to be a slope of -1, so something like that. And then over here, -1, -1, that -1 would get squared, giving us +1, divided by our -1 would give us -1 once again. So this is what our slope field would be at those 8 points for the differential equation they gave us. That's part A. Let's move on to B. Find the particular solution y equals f of x to the differential equation with the initial condition that f of 1 is equal to -1. This looks like a separable differential equation. The idea for these is I'm trying to get all of the x's on one side. I'm trying to get all of the y's on the other. So what I'm going to do is I'm going to divide by y squared on both sides, and I'm going to multiply by dx on both sides. If we do that, that's going to give me 1 over y squared dy is equal to 1 over x dx. Now at this point we see that all of our variables are separated, right? All the y's are on one side, all the x's are on the other. So we're going to move on to the second step, which is going to be to take the integral of both sides. We're going to need to anti-differentiate. But in order to do that, we need to recognize that the left side of this equation is the same thing as y to the -2 dy. And that's going to be equal to the integral of 1 over x dx. If we do that on that left side, we're going to need to add 1 to our -2. That's going to give us -1. And then we're going to divide by that new exponent. So we get y to the -1 over -1 is going to be equal to the antiderivative of 1 over x is one of our special ones from Chapter 6. That's going to be the natural log of the absolute value of x plus our c for that. Next, what we're going to want to do is we're going to try to find out what the c value needs to be, right? They gave us an initial condition, so we should be able to plug in 1 for our x here and then -1 for our y, and then hopefully try to find the answer for what c is going to be. If I simplify before we plug in, we get -1 over our y is equal to the natural log of the absolute value of x plus c. So substituting in -1 over -1 is equal to the natural log of 1 plus our c. -1 over -1 is +1, and the natural log of 1 is 0, so that means that our c has to be equal to 1 here. Ultimately then, we can plug back into our equation, so essentially from here, Negative 1 over y is equal to the natural log of x plus our c, which is 1. I'm going to get rid of this negative sign on both sides by multiplying by negative 1 to give me now 1 over y is equal to the negative natural log of the absolute value of x minus 1. And then our last step here to get that y out of that denominator, I'm going to take the reciprocal of both sides. And that's going to give me my final answer, which is y is equal, actually I'll put a line, y is equal to 1 over the negative natural log of x minus 1. And that would be our final answer for the particular solution for this differential equation that goes through 1 comma negative 1. That's going to be it. Part C, write an equation for the tangent line to the curve y equals f of x through the point 1 comma negative 1. Then use your tangent line equation to estimate the value of f of 1.2. All right, so at this point, we know we are well familiar with point slope form. The idea here being that if I'm writing the equation of a tangent line, that we use this form. So y minus y1 is equal to m times x minus x1. And we take a look what we have. We have our point. They actually gave it to us. They told us that that was 1 comma negative 1 in this problem. And the slope, luckily for us, we can use our differential equation in order to calculate what that slope is, right? We know that dy dx, the derivative, is y squared over x. So if we substitute in, right, into that y squared over x equation, that's going to be negative 1 squared over 1, which is 1 over 1, or just 1 for that. So with this information, I'm going to be substituting into my point slope form. This looks like this should give me y plus 1, because it's y minus negative 1, so y plus 1 is equal to 1 times x minus 1 for that. So that is going to be our equation of the tangent line. And our last part here is they're asking us to estimate the value of f of 1.2. So I want to plug in 1.2 for my x. I want to see what happens. So y plus 1 is equal to 1 times 1.2 minus 1. So y plus 1 is equal to 1 times 0.2. So y plus 1 is equal to 0.2. And if we subtract 1 from both sides, we get that y is equal to negative 0.8. So we can estimate that f of 1.2 is around negative 0.8 if we use this tangent line. That's part C. Let's move on to number 2. Number 2 says the rate of change of the volume V of t of water in a swimming pool is directly proportional to the cube root of the volume. So this is one where, they're asking us to write a differential equation that models this situation. Back from like 7.1, we did some problems that were like this. They're saying the rate of change of the volume, so that's going to be dv dt. That's the rate of change of volume with respect to time. And they're saying that it is directly proportional. So it is directly proportional to the cube root of the volume. So if we're saying that it's directly proportional, that means it's going to be some k value times something. And what's that something? Well, they're saying it's the cube root of the volume. So the cube root of the volume. And so this is what our differential equation would look like. But we notice here that they told us that v is 27 feet cubed and dv dt is 5. This information here is going to allow us to actually find that value of k. So if we do that, we can go over here and we can say, okay, well, dv dt is 5. And we don't know what k is, but we're going to take the cube root of our v, of our volume, which is 27. So 5 is equal to k times the cube root of 27. Cube root of 27 is going to be 3, which means if I want to get that k by itself, we need to divide by 3 on both sides. So k is going to equal 5/3 for that. So what's our differential equation? We've got dv dt is equal to 5/3 times the cube root of v. And that's going to be our equation for this problem. Nice. Number 3, find the general solution of the differential equation. Both of these problems look like separable differential equations from our 7.6 lesson. let's get all the y's on one side, let's get all the x's on the other. If we multiply by y on both sides, we're going to get y dy is equal to, if we multiply by dx on both sides, we're going to get 2x dx. Next, now that our variables are separated, we're going to take the integral of both sides and anti-differentiate. So that's going to give us y squared over 2 on that left side. And on that right side, we're going to get x squared plus c. Next, we want to get that y by itself, so we're going to multiply by 2 on both sides. So y squared is equal to 2x squared plus 2 times c. 2 times c is still a constant, so we're going to still just call that a constant. And then to get that y by itself, we need to take the square root of both sides. But keep in mind, it could be plus or minus. So plus or minus the square root of 2x squared plus c would be our equation for this. And again, what are we finding? We're saying that this equation, this y equation, if we took the derivative, would have the derivative dy dx is equal to 2x over y. So good to know, good to be able to find. Let's try number 4. Next up, we're going to multiply by dx on both sides, and I'm going to divide by y plus 4 on both sides. If I do that, that's going to give me 1 over y plus 4 dy is equal to x dx. Now that our variables are separated, we're going to take the antiderivative of both sides, the integral of both sides. And here on the left, since this is 1 over y plus 4, the antiderivative of that, if we find it, is going to be the natural log of the absolute value of y plus 4. That's going to be equal to the antiderivative of x, which is x squared over 2 plus our c. To get that natural log by itself, or rather get that y out of the natural log, we need to do the inverse operation of the natural log, which means we're going to raise to a base of e on both sides. And so we're going to have e raised to the natural log of y plus 4 is equal to e raised up to the x squared over 2 plus c. Here on the left side, because these are inverses, the e and the natural log cancel each other out, leaving me with just the absolute value of y plus 4 is equal to e raised up to the x squared over 2 plus c. To get rid of that absolute value sign, we're going to add a plus or minus to the right side, and then we're going to bring our c down as a coefficient in this term. So that's going to be y plus 4 is equal to c times e to the x squared over 2. The c is taking into account it could be positive or negative for that absolute value, so I'm not writing that plus or minus. I'm just leaving it as a c since the sign of it is not defined. But our last step here is we're going to subtract 4 on both sides to get our final answer, which is y is equal to c times e to the x squared over 2 minus 4 for problem number 4. Nice. Let's take a look at problem number 5. Problem number 5 says for each differential equation, find the particular solution that passes through the given point. So same idea for number 5 as we had for 3 and 4. 3 and 4, they asked for general solutions. Here, they're just saying find the particular solution. So it's the same steps as what we did up here, except we're going to find the exact c value for these problems 5 and 6. So in this particular one for problem number 5, what we're going to want to do first is we're going to want to, notice that for this equation that all the x's are already on one side, and our dy is the only y term that there is here. So I'm going to multiply by dx on both sides. We're going to say that dy is equal to 18 over 6x plus 3 plus 4 over x cubed, and I'll just put that dx here on the end. And what I'm going to do is I'm going to integrate both sides, but I'm going to integrate actually each part of both sides. I'm going to add an integral here, I'm going to add an integral here, and then one over here. The only thing that I'm going to keep in mind is that because these were both being added, this dx is technically on both of them, so I'll add a dx there as well for it. Here on the left side, if we take the antiderivative, what are we taking the antiderivative of? Whatever the coefficient of dy is, technically it's like a little 1. So if we take the antiderivative of that, we're going to get just y on the left side. On the right side, we could do a little bit of u substitution for this one if we were going to solve it. But ultimately, if we do that, we're going to end up getting 3 times the natural log of 6x plus 3 And then for this term, if we rewrite this as 4 times x to the negative 3 power, if we anti-differentiate, we're going to get negative 2x to the negative 2, which is the same thing as 2 over x squared, or negative 2 over x squared, plus whatever our c is. So now that we've taken the antiderivative of each of these parts, right, for each of these 3 parts, we want to find the particular solution. We're going to find the c value that we've got, which means we need to plug in the point that they gave us into the y's and the x's in this problem, and then use that to help us find our c value. So what does that look like? Well, our y here appears to be negative 15. That's equal to 3 times the natural log of 6 times negative 1/3 plus 3 plus negative 2 over negative 1/3 squared plus c. So negative 15 is equal to, what is this? Well, this looks like the natural log of 6 times negative 1/3 is going to be negative 2. Negative 2 plus 3 is 1, and the natural log of 1 is 0. So this whole term here is going to go to 0. And then we've got negative 2 divided by what looks like 1 over 9. So that's going to be negative 18 plus our c. If we add 18 to both sides, we get that c is equal to 3. So our particular solution for this, we're going to get that y is equal to 3 times the natural log of 6x plus 3 minus 2 over x squared plus 3. And that is going to wrap up number 5 for us. Number 6, we've got dy dx is going to be equal to 2y, and y is equal to negative 0.2 when x is equal to 0. This looks like an example of an exponential function. We know that because dy dx is equal to k times y. And we learned in our last lesson of chapter 7 that exponential functions, if we have things of this form, that we can sort of jump ahead if we recognize what form it is to say that we know that the solution is going to look like this. Y is equal to c times e to the kt power. What we can do here is we can say 2 things. We know we have an initial condition, but also the k value that we have is going to be the same k that's going to be here. So I know that y is going to be equal to c times e to the 2t. Again, that 2 is coming from right there. But to figure out what our c value is here, we're going to plug in x equals 0 or t equals 0 and y equals negative 0.2. So negative 0.2 is equal to whatever c is times e to the 2 times 0 power. Anything to the 0th power is 1, which means that our c then has to be equal to negative 0.2. So what is our final equation? Well, y is going to be equal to negative 0.2 times e to the 2t power. And that's going to be our equation for problem number 6. And actually, probably realistically, this should be a x instead of a t. You want to be consistent with whatever variables they're giving you. So maybe we should change that to be a 2x for that. All right, number 7, population growth. Population y grows according to the equation dy over dt is equal to ky, where k is a constant and t is measured in years. If the population doubles every 12 years, then what is the value of k? All right, we recognize once again that this is of dy over dt is equal to ky is an exponential function. And we know that all of the equations for that, the y equals, are going to be of the form y is equal to c times e to the kt power. But we don't know what the k is, so we need to look at the information they're giving us to help us try to find out what our c value and what our k value need to be here. And so let's think about how we can use this information to write some coordinates. If the population doubles every 12 years, what's the value of k? So the population is going to double every 12 years. Let's think about coordinates we could have. So let's say in the 0th year when this is starting, that there was just one person, or one thing that's being counted, or 1,000 people. In 12 years, then we're going to have double that, so 2. So we've got years, and we've got the population. Now, realistically, you could use any coordinates that you want, as long as they're spaced 12 years apart, and the population doubles in that time, because when we plug in, let's see what happens. First, let's plug in 0, 1. So if we plug in 0, 1, we've got 1 is equal to whatever c is times e to the k times 0. K times 0 is 0. E to the 0 power is going to be 1. So that tells me that c is going to be equal to 1 for this. Knowing that, we can say that y is equal to 1 times e to the kt, and we can plug in our second coordinate here. So we could say 2 is equal to 1 times e to the k times 12. We can then divide by 1 on both sides, or just say multiplying by 1 doesn't change it. And in order to get the k down out of the e, we're going to need to take the natural log of each side. So ln of 2 is going to equal 12k. So if we want to get that k by itself, we need to divide by 12 on both sides, which means that k is going to be equal to the natural log of 2 over 12, which for this one, if we use our calculator, ends up being about 0.058 if we're rounding to 3 digits after the decimal place. Great. Let's try number 8. So explain why the following slope field cannot represent the differential equation dy dt is equal to 0.4y. This is one that we've seen pretty similar to earlier in the chapter when we were talking about slope fields. There's a couple different arguments you can make for this. One that I'm going to use is I want to imagine looking at all the same y values. So I notice that this equation has only a y in it on that right side, which means that the x should not affect the slopes. And what I notice over here is I'm looking at these different coordinates and I'm seeing, hey, okay, this is 0, 4. Over here we've got like, maybe not right there exactly, but somewhere around there is like 2, 4. Over here we've got like 4, 4. What I notice is that if I were to calculate the slopes at each of these, for these slope fields, I should be getting the exact same y value each time. 4 times 0.4 would be like 1.6. And I see something close to 0, and then I see these values changing. But these should all just be 1.6 because the y value is the only thing that should matter for this equation. So what I can notice for one of my possible answers here is I can say that I notice the slope field changes when y stays the same and x changes. So that would mean in this case that whatever equation for our differential equation needs to have both an x and a y in it if it was going to work. So that is something that disqualifies this. This could not be the slope field for this graph. But one other possible thing that we could talk about is we could take a look at the x-axis. These are all places where y is equal to 0, right? The x-axis at each of those coordinates that are on here. And if this is our differential equation, if we plugged 0 in, we would expect 0 to be the dy dt for every single value on here. And we see that it starts off at 0, but other values don't have 0 for each of those. So what we can mention here is when y is equal to 0, dy dt should equal 0, but it does not in the graph. Great. So those are two possible solutions. Really, either one is reasonable for this. Let's talk about number 9. So for the value of k, if any, will y equals k times cosine of 2x plus 3 times sine of 4x be a solution to the differential equation? Y double prime plus 16y is equal to this negative 6 cosine of 2x. So I notice that this equation has a y double prime in it. So my first step here is I want to take the first and second derivative. So y prime is going to equal, if we take that derivative, negative 2k sine of 2x plus 12 cosine of 4x. So using a little bit of chain rule on each of these as I'm taking that derivative. And then if we take this second derivative, y double prime is going to equal what looks like negative 4k cosine of 2x minus 48 sine of 4x. So for each of these, I'm essentially multiplying by 2 here to get this on the outside. Here I'm multiplying by 4 to get that 48. But this is my first and my second derivative for this equation for y. So what I'm going to do is I'm going to take what we've got here and we're going to plug in. I've got y double prime plus 16y should be equal to negative 6 cosine of 2x. If we substitute in for those, our y double prime is this. So that's going to be negative 4k cosine of 2x minus 48 sine of 4x. And then we've got plus 16y. So plus 16y, and y was this original equation here. So that's going to be 16 times k cosine of 2x plus 3 sine of 4x. And that should be equal to negative 6 cosine of 2x. What I'm going to do next is I'm going to distribute. Looks like here that this 16 can multiply both of these terms. If we do that, we've got negative 4k cosine of 2x minus 48 sine of 4x plus 16k cosine of 2x plus 48 sine of 4x is equal to negative 6 cosine of 2x. We can see here that our 48 sine of 4x and our negative 48 sine of 4x are going to cancel. We also notice that we've got a k cosine of 2x in both of these terms, which means that they are like terms. So if we want to combine them, we're going to take negative 4 plus 16. That's going to give me 12k cosine of 2x. And that's going to equal the right side, which is negative 6 cosine of 2x. Divided by cosine of 2x on both sides, we get 12k is equal to negative 6. And if we divide by 12, we get that k is equal to negative 6 over 12, which is negative a half. So that is going to be our final answer for problem number 9. Happy studying. Good luck on your Chapter 7 test. Have a great rest of your day.